Okay, so we are talking about all pair shortest path. We have seen two algorithm dynamic programming based approach like last class we have seen the Floyd-Warshall algorithm. So, today we will talk about some application of the Floyd-Warshall algorithm, that is to find the transitive closure of a graph, and then we will move to the another algorithm for finding the all pair shortest path. It is called Johnson algorithm, but this will be using the old algorithm like we know Dijkstra's algorithm. So, let us first talk about the applications of Floyd-Warshall. So, just to recap, so Floyd-Warshall algorithm. So, it is basically sorry, R is missing, ARS. Okay. So, this is basically to find the all pair shortest path. All pair shortest path. So, now we have seen, suppose we have given a graph G V comma E. Now, so this is a directed graph or direct graph, and we have a edge weight E to R. Okay. So, now so suppose V is basically V1, V2, Vn, and we denote delta uv is the weight of the shortest path from u to v if it is exist, otherwise it is infinity. Weight of the shortest path from u to v if it is exist, otherwise it is infinity. If there is no shortest path from u to v. Okay. So, basically our aim is to find these deltas. So, delta of I j. So, this delta of I j is basically delta of u I v I v j. So, our vertex are this v I v j. So, this we are denoting by delta of I j. So, is to simplify, we denote the vertexes as from 1 to n. So, basically delta of I j is the weight of the shortest path from v I to v j. It could be infinity also if there is no shortest path. So, for Floyd-Warshall, what we did to find out this delta? So, we have defined, so this we have discussed in the last class, just to recap. So, we have defined the C I j, the recursive relation C I j k is the minimum of this is the basically weight of the shortest path, weight of the shortest path from path from I to j, v I to v j, such that the level, the intermediate node vertices are belonging to the set 1 to k. Okay. So, that means we are at ith node, we want to go to jth node. So, we will see some vertices in the middle in the path like this dot 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 this. So, these are the intermediate nodes in the path from I to j. So, we want the level of these nodes from 1 to k. So, So, this is Cij. So, all the vertex level must be less than k, less than equal to k. Okay. There is no restriction on I and j, but in the middle the vertices we are visiting, they must be level from 1 to k. I mean, we should not see any vertex whose level is more than k. So, we should not see a vertex whose vertex v k plus 1 say, or k plus 2. So, that is how we define Cij k. Now, if so, basically what we have? We have Cij. So, what is the recurrence for Cij? So, Cij 0 is basically Aij, the adjacency matrix. Adjacency matrix means that adjacency. So, Aij is Wij if Ij is an H, it is Wij if Ij is an H, otherwise we have infinity. Yeah, so otherwise, so what is Aij? Aij is otherwise it is infinity. So, basically Cij is what? Cij 0 is basically what? Cij 0 means we are at ith level. Now, in the middle we want a vertex whose size is less than equal to 0, but our vertex start from 1. So, we do not want any vertex. So, if there is a direct edge from I to j, and then that will be the basically Wij. So, it is basically Aij if it is. So, it is basically the adjacency matrix coming from adjacency matrix. So, this is the Cij 0, the initial condition, but what is the Cij I, Cij k. So, this in the last class we have proved that this is basically minimum among k such that Cij k minus 1, this and Cik k minus 1 plus Ckj k minus 1. Okay. So, minimum among these. So, from this we have the algorithm divide and conquer approach. So, that is Voigt-Warshall algorithm. Voigt-Warshall algorithm. So, what is that? So, this is basically taking a graph with the matrix A. A is the adjacency matrix. So, this A is basically consists of Aij n cross n matrix. This is the adjacency matrix. Okay. So, basically we initialize by C if we denote this C matrix. So, what is the advantage of getting C? If we know C, because we are looking for delta. So, delta is basically delta matrix is basically delta Ij. So, we are looking for delta. So, what is the relationship between delta and C? Now, if we can find out all Cij k recursively, kind of dynamic programming technique. So, basically Cij n, because our vertices start from 1 to n. So, Cij n is basically giving us delta Ij. So, Cij n is basically giving us delta Ij. Okay. So, that is why if we somehow can find out all the Cij's for all k from 1 to n, then we got the deltas. Anyway, so this is the initialization step. So, we want to find the C. So, this is the C matrix which is initialized by A matrix. Okay. Then we have this formula. So, for I is equal to 1 to k, for k is equal to, this is Cij k. So, basically we can write Ck initialized by this, but we are using the same variable. So, we are just doing 0 to n, then for I is equal to, for I is equal to 1 to n, and then again for j is equal to 1 to n. This is 3 for loop. What we are doing? We are testing the value of Cij, what we have already. So, this is initialized by Cij is 0, then we are looking for Cij 1. So, now if this value, if Cik is plus this 0, if this is less than this Cij 0, then we must have this in our Cij 1. So, that is the formula. So, do if Cij, if this is greater than Cik plus Ckj, then Cij is replaced by Cik plus Ckj. Okay. So, this is the Cij is replaced by Cik plus Ckj. So, this is the minimum one, we are storing this. We can add a k over here, but that k is basically in the superscript, but we are getting this here. So, this is the formula to finding Ciks, and finally, the C matrix will be our delta 1, 2, 3, 4, 5, 6, 7. Now, that is our delta. So, delta is basically the C matrix. So, this is what we are looking return. Okay. So, this is what we are looking for. So, this is what we have. This is called the White-Warsall algorithm, and the time complexity for this is basically we have 3 for loops. So, time is order of n cube algorithm. So, now we will talk about an application of this algorithm, which is called transitive closure of a graph. So, suppose we have a graph, it is a directed graph, and here there is no weight on the edges. So, this is called transitive closure of a graph. Transitive closure of a graph. Okay. So, suppose we have a graph G. So, say V is say V1, V2, there are say n vertices, and for simplicity we are writing vertex labeling as 1 to n. Okay. So, vertex are from 1 to n. Now, so we define Tij to be 1 if there is path from ith vertex to jth vertex. If there is a path 1, if there exists a path from I to j, otherwise it is 0. That means no path from I to j. So, that means if you have vertex I and if we have a vertex j, okay, then if we have a direct edge, that means there is a path. So, that is also in, but we are not looking for only direct edge, we are looking for if from starting from ith vertex, if at all we can reach to a jth vertex. So, that is the idea. So, that is the transitive closure. So, if there is a path from I to j, then Tij is 1. Okay. So, some path, I mean, so this is the matrix we need to find out, the Tij matrix. Is this problem clear? So, we have given a graph, this graph is a directed graph or diagraph. We have given a graph and we defined a Tij which is basically 1 or 0. It is 0 if there is no path from I to j. It is 1 if there is a path, we start from I, if there is a physical path to j, then this value is Tij value is 1. So, basically we want to find this Tij. So, how we can get this Tij? So, we want to basically use the White-Warsall algorithm to have this Tij. So, what is the idea? So, idea is to use the instead of minimum and plus, we will just use the or and operation. So, that is the idea. Idea is to use the Voigt-Warshall algorithm Voigt-Warshall, but with the operation logical or and instead of minimum or plus. Okay. So, we remember the algorithm, like we have this Cij, k is basically minimum of Cij k minus 1 comma Cik k minus 1 plus Ckj k minus 1. Okay. So, instead of this minimum, we will use the OR operation, and instead of this plus, we will use the AND operation. So, that means either present or absent, this is the logical operation. So, either present or absent. So, like as if we just give the weight of each vertex, because there we are not concerned about the weight of the graph. We have given a graph G which is V comma E, V1 to with the V. So, our concern is we have to find, so Voigt-Warshall will find delta Ij. So, this is basically Cij in. So, instead of find delta Ij, what we are looking for, we are trying to find Tij. So, basically if we run Voigt-Warshall, the algorithm we have discussed, with these two operation, this is the logical OR and this is the logical AND, then this will give us Tij. Why? Because if we just add a weight 1 to each of the edges, then there is a path, means there is a shortest path. So, we are not bothered about shortest path here, we just bother about whether there is a physical path from I to j. So, if you run this for all the vertices, this is for all the vertices, because vertex number is up to n, then eventually this will give us Tij if it is exist, and if the delta is z infinity, then the corresponding Tij. If there is, that means that delta infinity means there is no shortest path, because here weight we are assigning 1 to each of the edges. So, there is no question of negative weight. So, if delta is basically infinity, then the corresponding Tij is, I mean basically 0. That means there is no path from I to j. So, that is the idea. So, this is the application of Voigt-Warshall on the transitive closure. Okay. So, now we will talk about another application. So, means another algorithm which is called Johnson algorithm to finding the all pair shortest path. Okay. So, let us talk about another approach to finding Johnson's algorithm. Okay. So, this is to find the all pair shortest path. So far we know some dynamic programming technique to find the all shortest path. Now, if we use the Voigt-Warshall, we know. So, suppose you have a graph G, V comma E, and V is a vertex, set of vertices. This is 1 to n. For the simplicity, we are assuming vertex as numbering as 1 to n. Now, we have seen for Bellman, so we want to find out the all pair shortest path. All pair shortest path. Okay. Now, we want to see whether we can use the algorithm we already know, like single source shortest path algorithm. We know two single source shortest path algorithm, one is Bellman-Ford, another one is Drexler's. But Bellman-Ford we have seen, Bellman-Ford will give us, if we run the Bellman-Ford, yeah, Bellman-Ford. So, if we use Bellman-Ford, so this is basically a single source shortest path. Then Bellman-Ford itself will take order of n square for a single source, and we have to run for all the source, all the vertices. So, this will give us for all pair, this will give us for Bellman-Ford order of n cube. Okay. So, this is not good as the we already have order of n cube algorithm, n cube or n square, because this is we have to, this is maybe, yeah. So, no, this is n square, n cube, because Bellman-Ford is order of v into e, right. So, v is n and e is basically order of v square basically. So, this is n cube. So, this is n to the power 4. This is not as good as so Bellman-Ford if we run, say n to the power 4. But if we run Dijkstra's, but for Dijkstra's there is a restriction. Bellman-Ford can handle the negative weight edges because it can handle the negative cycle, but Dijkstra's cannot handle negative weight cycle. So, somehow if we know that our graph is having no negative weight edge, then one can try for Dijkstra's. So, if no negative edge, negative weight edge, so this implies no negative cycle. This implies we can run Dijkstra's. Okay. Now, if you run Dijkstra's for all pair shortest path, so Dijkstra's will take how much time? The Dijkstra's is also single source shortest path, single source. So, now one run of Dijkstra's will take order of, it depends on which data structure we are using. So, if we use the Fibonacci heap and the worst case amortized analysis we have seen, it is order of v log n, log v, sorry. Now, this is basically order of E is order of v. So, this is basically order of anyway, let it be. So, now if we run it for all pair shortest path, then it will be for all pair, it will be order of v into E plus v log v, sorry, v square log v. Now, this is same as, this is as good as the Voigt-Warshall, because this is at most order of n cube, but sometimes if E is not order of n cube, then it is less. Okay. So, depending on E, it will be either order of n cube or order of n square log n. So, this is good. Now, the problem is here we have this assumption. So, there should be no negative weight edge. So, how we can do that? So, to ensure that, we have to do something called graph relabeling, reweighting. Graph reweighting. So, this is just to ensure there will be no negative weight edge. So, we are going to label the vertices. We are going to, this is a theorem. We are going to, suppose there is a label, given a label HV, okay, for each vertex V such that we reweight the graph, reweight the edge, reweight each edge UV belongs to E by, so W hat UV is equal to, so it was having a original weight WUV, then plus H of V minus H of U, okay, WUV, then plus H of V minus H of U. Okay. So, basically what we are doing, we have a two vertex, this is WIV Now, we are labeling the vertices by h. H is a function, h is a function, we have to get this function. We will come to know how we will get this function. H is a function such that, so we are labeling this by h of u, we are labeling this by h of v. Now, this we are rewriting as w hat iv is basically w, the original weight, then plus the difference between their weight. So, this way we are rewriting. So, if we rewrite this, then okay. So we rewrite all the vertices, all the path, all the edges like this. If we do that, then suppose we have a path p from V1 to Vk. Suppose we have a path, any path, let us take a path p from this. Now, what is the weight of this path? Weight of this path is basically w of summation of w of weight of this like this. So, w of vi to vi plus 1 or vi minus 1 to vi plus 1, say I plus 1, and I starting from say if it is say k plus 1 to k, say. Okay. So, if you do like this, then what is the, this is the original weight of the path. Now, what is the new weight of the path after the relabeling of the weight? So, this will be basically, so we relabel each of this. So, this is basically summation of, this is relabel as w of, so we relabel each of this. So, w of vi plus v of I plus 1 plus h of v of I plus 1 minus h of vi. So, if we I is from 1 to k. So, if we do this, or if we put this k, then we have to take it as k minus 1. Anyway, this is just a notation. So, if we just take this, this will be basically w of p plus the h of, so this will give us a vk minus h of v1, vk minus h of v1. Now, we want weight of each path, there should not be any negative cycle. So, we want weight of each path should be positive. So, that means we want to choose the labeling. So, this is the new path. So, new path will depend on this. So, we want to choose the labeling in such a way that for all the edges wv must be greater than 0 for all uv belongs to E. Okay. So, for that what we are doing? So, so this is nothing but what? This is w of uv plus h of v minus h of u. So, this we want greater than 0. So, that means what? That means we want w of, we want basically, so this we take this side. So, w of u minus w of v is less than equal to w of uv. So, this we want for all the vertices. We want to have a h function. So, this h is basically how come we got this h? So, we can get this h from the this is the solving the different constant. Okay. So, like we have seen x1 minus x2 is less than equal to wi want to like this. So, solving that is, so again we can apply the Bellman-Ford algorithm to solve this difference constant. Using the Bellman-Ford algorithm, we can get this h using Bellman-Ford. So, using Bellman-Ford algorithm we can get this H. So, this will take Bellman-Ford will take order of n cube say, okay, V comma E, and then once we relabel it, then we know that there will be no negative weight H in the graph, then we can run the Dijkstra's. So, after relabeling, once we got the solution of this, then we relabel the these edges, we got the H, then we relabel the edges. Once we relabel the edges, then we apply, this is the first step. So, once we relabel the edges, then the next step is we apply the Dijkstra's for all pair shortest path, because there is no negative cycle, and this will take time for all pair, order of V into E plus V square log V, if we use the data structure Fibonacci heap and that amortized analysis. Okay. So, now we got a path, but this path is basically shortest path is WP. Now, from WP we need to get back the W, right, W hat P, we need to get back the WP. So, that we have the formula, W hat P is basically WP plus H of Vk minus H of V1, and this will take. So, we know this. So, basically WP is basically H WP hat minus H of Vk plus H of V. So, we know this function H and we know this y step 2, then we get the this. So, the run time is basically this one. So, this is the way, because we want to use the Dijkstra's algorithm, because Dijkstra's algorithm is time complexity is good compared to all other algorithm like Bellman-Ford. So, we want to use Dijkstra's, but for that we need to have this no negative weight H. For that we need to reweighting the graph. So, this algorithm, this idea is by Johnson's idea. Okay, thank you.